Have you ever wondered how instruments produce sounds? Just like how the violin, harp, drums, piano, and xylophone produces melodies or symphonies. How about televisions? Do you know how they work? Have you ever wondered how a single screen is able to show different scenarios and with different channels?
The answer is simple. It was possible through mathematics. And how, you ask? Let us explain by discussing
Ian Stewart's Nature's Numbers, specifically Chapter 5 entitled From Violins to Videos.
This chapter opens up with a story on how applied mathematics and pure mathematics joined together to the creation of something that is more powerful and compelling than what could have been made by either of the two alone. And it began at the start of the 16th century with a problem of the vibrating violin string. A single violin string that was plucked produces vibrations. According to the Greeks, the way in which the string of the violin vibrates depends on the manner of how it has been plucked. It has been later on realized that the pitch of the tone of the violin is determined by the frequency of vibration. Brock Taylor, an English mathematician, published a book in 1714 about the fundamental congregational vibrational frequency in terms of its length, tension, and density. Each frequency corresponds to a different configuration of the moving string, and the same string can take up many different shapes. This idea that was from the Greeks was evidenced through a presentation of how the pitch of the violin is dependent on the nodes.
From this chapter, it showed us that the simple strum of a violin string would cause a chain of reasoning and discoveries. As a matter of fact, Jean Le Rond d'Alembert first claimed that the shape of wave can be anything you like. However, Leonhard Euler figured out the wave equation as a response for D'Alembert's work. Euler and Bernoulli's work conclude that the basic vibration components are the sinusoidal wave that led to the formulation of the wave equation. After the formulation of the wave equation that was first introduced by vibration of violin string, the next instrument that helped make a better formula was the drum. The next sequence of the event was moving out from instrument, which led to the discovery of an equation denoted as the most important mathematical formula, which is Einstein's famous relation between mass and energy. And a big game changer of this formula was when it was utilized in electricity and magnetism.
Michael Faraday was fascinated by electricity and magnetism. He knew that electric current would hold a magnetic force and that is a magnet that could produce an electric current. So, by 1831, he succeeded and showed that electricity and magnetism are two aspects of electromagnetism. Later on, the successor of Faraday, James Clerk Maxwell, used a mathematical equation to describe Faraday's distribution of magnetic and electrical change throughout space. So by 1864, he defined his theory down to four differential equations: Gauss' law for electric fields, the corresponding formula for magnetic fields, Faraday's law of magnetic induction, and lastly, Ampere's law plus Maxwell's displacement current. Maxwell's four equations describe the electric and magnetic fields arising from distributions of electric currents and charges and how those fields change in time. They were the mathematical distillation of decades of experimental observations of the electric and magnetic effects of charges and currents, plus the profound intuition of Michael Faraday. Maxwell's own contribution to this equation is just the last term of the last equation, but the addition of that term had dramatic consequences. It made evident for the first time that varying electric and magnetic fields could feed off each other. These fields could propagate indefinitely throughout space, far from the varying charges and currents where they originated. Hence, these four theories revealed a clear symmetry between electricity and magnetism, each affecting the other in a similar manner. Moreover, the wave equation implied that these electromagnetic waves traveled with the speed of light, For instance, Heinrich Hertz was able to generate electromagnetic waves at a frequency, producing what we call radio. Televisions and videotapes soon came after, then the rest is history.
It has been conventional for mathematics to be categorized into pure and applied. This categorization baffled the great mathematicians of all time because for them, math is math. It is a fascinating historical recap of how their contributions have led us to advantages in all aspects of life. Due to a violin spring that take inspiration for the formulated equation, which turned out to be useful in mapping electricity and magnetism. And that's how mathematics can start from what we think is just a simple thing in life, but then turn into a series of complicated yet meaningful discoveries.